Hi friends, welcome back. In the previous session, we have completed Fourier transform in that one topic, which is a sampling theorem also. And in the next this hour, we are going to see Laplace transform. So try to understand what I am saying. Suppose if I consider the Fourier transform, what the Fourier transform is doing actually, it is going to give you the frequency content of the given signal. That means if you want to know what are the frequencies it is having, then at those frequencies how much the amplitude we are having. These things can be said by using the Fourier transform. But in the Fourier transform, we haven't discussed about the system, suppose whether it is a stable system or a causal system, and these kind of things we haven't discussed. And one more thing, we haven't suppose we are having a integral differential equation, then we haven't converted that into algebraic equations also. So these are the defects in the what we can say Fourier transform, and same things which are advantages for the Laplace transform. So that means by using Laplace transform, we can convert a differential equation into algebraic equation. That is one advantage of the Laplace transform. And another advantage is we can determine stability, causality of a system actually. But there is a drawback in the Laplace transform, which is nothing but we cannot determine frequency content of the given signal. That is already done by Fourier transform. So that is the difference between Fourier transform and a Laplace transform. So I hope you understood. So let's say we are having two types of Laplace transform. One is bilateral Laplace transform, another one is a unilateral Laplace transform. So let's see one by one. Just you can take this one so that you can understand it later when we complete the Laplace transform. These things can be understood very simply. So Laplace transform is of two types. One is bilateral Laplace transform. So in the bilateral Laplace transform, suppose x of s is nothing but integral minus infinity to infinity x of t e power minus st dt. This is the way we can calculate bilateral Laplace transform. Then what is the advantages here and what are the important points, key points in the bilateral Laplace transform? Here we can determine causality and stability of a system. This is the one thing which bilateral Laplace transform will do. And here we will consider ROC concept. And here no initial conditions. These are the key features of bilateral Laplace transform. Even though if you don't understand, still take it, because when we complete the Laplace transform, you can understand these points in more clear way. Okay. Next, we are having unilateral Laplace transform. The unilateral Laplace transform is defined integral 0 to infinity x of t e power minus st dt. Here we can write a integral differential equation with initial conditions into algebraic equation. Integral differential equation can be converted into algebraic equations. That is the one thing unilateral Laplace transform will do. And here no ROC concept. We don't worry about the ROC concept. What is ROC? We will see later. No ROC concept. Here initial conditions are considered. Initial conditions are considered. So this is the difference between bilateral Laplace transform and unilateral Laplace transform. First you can take these things, then we will enter into bilateral Laplace transform. What is this ROC concept? These things we can see, how we can determine causality, stability, this. So first take down these things, then you can understand them later. Okay, take it. So let's see bilateral Laplace transform. First we will consider bilateral Laplace transform. So for this, suppose if time domain signal is given to you, we can calculate x of s. What is x of s? X of s is equal to integral minus infinity to infinity x of t e power minus st dt. So here what is s? S is equal to sigma plus j omega, and this s is nothing but complex frequency. Complex frequency. If I ask what is the real frequency in this one, so many people will say sigma. No, it is not the real frequency actually. So have you ever seen the frequency in terms of sigma? No, we will always see frequency in terms of omega. So the imaginary part is going to give you the real frequency. Real frequency. Real frequency. Then what is sigma indicate? This is called as Napier frequency or attenuation constant, we can say like that, attenuation constant. Okay, now if I replace s, x of s is equal to integral minus infinity to infinity x of t e power minus sigma t e power minus j omega t dt. So here we can write, suppose if I take this part, we know from the Fourier transform of any signal can be calculated, signal multiplied with e power minus j omega t, integration from minus infinity. So this integral indicates Fourier transform of this signal. So that means it is simply equal to Fourier transform of x of t e power minus sigma t. So remember, Laplace transform of x of t is the same as Fourier transform of x of t e power minus sigma t. So this is the relation between Laplace transform and Fourier transform. Now, what if sigma is equal to 0? Sigma is equal to 0. Then that implies s is equal to j omega. S is equal to j omega. S is equal to j omega. So here then Laplace transform of x of t is equal to Fourier transform of x of t. So this is a very important point. Here this is very advantageous and people do mistakes also here. What is the advantage? What is the mistakes we can do? So here so many people will say, whenever you know Laplace transform, in that one if I substitute s is equal to j omega, that will become Fourier transform. Yes, definitely whatever you said is correct. That means If you substitute S is equal to j omega, then Laplace transform will become Fourier transform. Okay, I can agree with that. But is it true? No, it is not always true. Why? Suppose let's say I will take just example only. Examples. E power minus at u of t. For this, what is x of s? Because everybody knows it, I am just asking. This is 1 by s plus a. Then what is x of omega? If I replace s is equal to j omega, then j omega plus a. Yes, this is the what the Fourier transform for this signal. We know this one. Okay, no problem. Correct only. What if I take u of t? U of t. For u of t, x of s is equal to 1 by s. Then what is x of omega? If I replace s is equal to j omega, this is what we are going to get, 1 by j omega. But what is x of omega for u of t? That is 1 by j omega plus pi delta omega, which is wrong. So I hope you understood. Next, suppose if I take r of t, then what is x of s we are going to get? This is 1 by s square. Then what is x of omega we are going to get by substituting s is equal to j omega? That is j omega whole square. That is minus 1 by omega square. Minus 1 by omega square. But what is the Fourier transform for this? But x of omega does not exist. Why does not exist? Because it is a ramp function and it is having unbounded nature. So if it is an unbounded signal, Fourier transform does not exist. So from this you can understand, in this kind of signals, if I replace s is equal to j omega, I can get Fourier transform. But in this case and in this case, we don't get this one. So in general, if I categorize these signals, this is a energy signal, this is a power signal, it is a neither energy nor power signal. So in power signal and neither energy nor power signal, if I place s is equal to j omega, I cannot get the Fourier transform. But in energy signal, if I replace s is equal to j omega, I can get the Fourier transform. That's what you have to remember. So definitely from this we can say, yes, if I substitute s is equal to j omega, I can get Fourier transform, but the signal must be energy signal. So I am getting that point. Observation. What is that? By replacing s is equal to j omega, we can get Fourier transform from Laplace transform. But the signal must be energy signal. But the signal must be energy signal. So remember that. So here this is a energy signal. This is power signal. And this one neither energy nor power. That's why we don't get it. Okay, take it. So I hope you understood. The relation between Laplace transform and Fourier transform is this one. So x of t Laplace transform is same as Fourier transform of x of t e power minus sigma t. Clear? Take it. How S-plane looks like? Here x-axis is called as real axis, y-axis is called as j omega axis, and we can call this entire portion as left half of S-plane. This entire thing is LHS, left half of S-plane, and this one is called as right half of S-plane, and this is a j omega axis or imaginary axis, which is a reference axis, which is called as reference axis. Reference axis. On this reference axis, omega value is changing from minus infinity to plus infinity. So here, so if I say omega is equal to minus infinity, omega is equal to 0 here, omega is equal to infinity. The range of omega, minus infinity plus infinity. Clear? Take it. Next, convergence condition for Laplace transform. Convergence condition for Laplace transform. We know x of s is equal to integral minus infinity to infinity x of t e power minus sigma t e power minus j omega dt. Okay. What do you mean by convergence of Laplace transform? That means x of s value must be bounded. That means its value will never see infinity. That's what the meaning of convergence condition. So convergence condition of Laplace transform means Laplace transform should never be infinity at any value of s. So whatever the value of s you take, it doesn't matter, it will never go to infinity. Then we can call convergence of Laplace transform. So to get Laplace transform bounded, what is the condition on x of t? So here I can say from the Squarge inequality, mod x of s is less than or equal to integral minus infinity to infinity x of t e power minus sigma t modulus for this mod e power minus j omega t dt. And what is the modulus for this function is 1. So finally mod x of s less than or equal to integral minus infinity to infinity x of t e power minus sigma t mod dt. So to say x of s value bounded, this value must be less than infinity. So Laplace transform converges if this integral value is a finite value. So what do you mean by that? X of t e power minus sigma t must be absolutely integrable. Have you seen that in the Fourier transform? Yes, we have seen in the Fourier transform, for the convergence of Fourier transform, I told you x of t must be absolutely integrable. That means mod x of t must be absolutely integrable. So here we don't have to see x of t, we have to see x of t e power minus sigma t. I hope you understood. So in the Fourier transform, the convergence of Fourier transform is we have to observe x of t, whether x of t is absolutely integrable or not. If it is absolutely integrable, we can say Fourier transform converges. But to say Laplace transform converges, the signal what we have to consider is not x of t. It is actually x of t e power minus sigma t. We have to check this one. So x of t e power minus sigma t, if you check it. So if it is absolutely integrable, then we can say x of s is bounded, or we can say Laplace transform is going to be converges. So Laplace transform of x of t converges converges if x of t e power minus sigma t e power sigma t minus sigma t is absolutely integrable. Is absolutely integrable. So this condition has to be satisfied. So if this condition is satisfied, then we can say Laplace transform converges. Clear? Take it. Example. Here x of t is equal to e power minus 3t u of t. E power minus 3t u of t. So to say Laplace transform converges, what is the condition? Let's see. So for the convergence of Laplace transform, the signal what we have to consider is not x of t. What I told you, it is x of t e power minus sigma t. So what is x of t e power minus sigma t actually? So this is e power minus 3t e power minus sigma t u of t. So that is nothing but e power minus 3 plus sigma t u of t. Now you tell me, this signal has to be absolutely integrable. So you tell me e power minus 3 plus sigma t u of t. How it look like? It may look like this, or it may look like this also, e power minus 3 plus sigma t u of t. So if I say, out of these two signals, which one is absolutely integrable? That means if I take the absolute value, if I find the area under the curve, which has to be finite value. So if I find the modulus, it won't make any difference because it is a positive and real values. So if I calculate the area under this curve, it is going to be finite value. If I calculate area under this curve, it is going to be infinite value. So out of these two, so here 3 plus sigma is greater than 0. Here 3 plus sigma is less than 0. Because this value is going to be negative, then it is going to be exponentially growing. If this value is positive, then total value is negative, so it is going to be exponentially decaying. So to say which one is a absolutely integrable, this one is absolutely integrable. Absolutely integrable. This is not absolutely integrable. Okay, better I will write not absolutely integrable. So I can say, so we don't have to draw anything here, just to make you understand I am saying. Out of these two, which condition has to be satisfied so that it is going to be absolutely integrable? That means Laplace transform converges. So I can say Laplace transform converges if 3 plus sigma must be greater than 0. 3 plus sigma must be greater than 0. Even it should not be equal to 0. Why? If it is equal to 0, then this value will become 1. That is nothing but u of t. If it is u of t, so let's say, then what will happen? U of t means it is this one. What is the area under u of t? It is going to be infinity. So it has to be strictly greater than 0. So if it is strictly greater than 0, then we can say Laplace transform converges. Let's see. In S domain, sigma j omega. Where is sigma greater than minus 3? Sigma greater than minus 3. So here is the minus 3. And you don't have to take the minus 3 also, except minus 3. So then I can take a line which is like this. Okay. So sigma greater than minus 3. If I take sigma greater than minus 3, then this is what the sigma greater than minus 3. Okay. So this region where Laplace transform converges is called as ROC, region of convergence. This is called as ROC. ROC. This region, sigma greater than minus 3, is called as ROC. What is ROC? ROC is nothing but region of convergence. So in general, what is region of convergence? This is the range of sigma for which Laplace transform converges. Then we can call that range is called as ROC. So it is the range of sigma for which Laplace transform converges. So range of sigma means real part of S. So for what values of sigma we are going to get convergence, or we can say x of t power minus sigma t is going to be absolutely integrable. Then that region is called as region of convergence. Clear? Take it. E power 3t u of minus t. For this signal, find ROC. So find ROC. Find ROC. Okay. Now I told you, to calculate ROC, the signal what we have to consider is not x of t. It is actually x of t e power minus sigma t. So what is x of t e power minus sigma t? That is e power 3 minus sigma t. I am directly writing u of minus t. So for what values this is going to be? Suppose if it is positive, then we are having growing exponential in the left sided signal. So it is going to be bounded. So let's say this kind of curve we are going to get if 3 minus sigma greater than 0, and we can get this kind of curve when 3 minus sigma less than 0. So this is not the case, this is the case we have to consider, because for this it is we are going to get area under this curve is going to be finite value. So what is the condition? 3 minus sigma greater than 0, sigma less than 3, sigma less than 3. So if I draw that, sigma j omega. So here is the 3. So ROC is less than 3. So this is what the ROC is. This is what the ROC. Clear? Take it. X of t, which is existing between 0 to 2, whose value is equal to. Now, is it absolutely integrable? Of course, but this is not we have to consider. We have to consider x of t e power minus sigma t. So let's say x of t e power minus sigma t. It is having different things. What is that? Suppose e power minus sigma t, if sigma value is less than 0, greater than 0, equal to 0. Suppose if it is less than 0, sigma less than 0. If sigma less than 0, this is going to be a growing exponential multiplied with this one. Then how it is going to look like? Growing exponential. If it is multiplied with x of t, so it will exist only up to 2. Up to 2. So this is what we have. So if I try to calculate area under this one, so it is going to be a finite value. It is going to be a finite value. Next, suppose sigma greater than 0. If sigma greater than 0, then what will happen? Sigma greater than 0 means it is exponentially decaying function which is multiplied with x of t. So exponentially decaying function is multiplied with x of t means which is existing only between 0 to 2. So if I try to calculate area under this one, again a finite value. Next, suppose if I take another case where sigma equal to 0. If sigma equal to 0, that is nothing but x of t only. Then we are going to get this one 0 to 2, 1. If I try to calculate area under this one, so this is also finite value. Finite value. So if I take different values of sigma, maybe less than, greater than or equal to 0, for all the values of sigma, we are getting always it is absolutely integrable. So for all values of sigma, x of t e power minus sigma t is always absolutely integrable. That means, can I simply say for all values of sigma, we are going to get convergence of Laplace transform? Can I simply say Laplace transform converges for all values of s, or we can say ROC is nothing but entire s plane. So I can say for all values of sigma, comma, x of t e power minus sigma t is absolutely integrable. Is absolutely integrable. Absolutely integrable. That implies what is ROC? ROC is entire S plane. Entire S plane. Entire S plane. Clear? Take it. So till now we have seen 3 curves. So what are they? Summary. X of t is equal to e power minus 3t u of t. For this one, what kind of ROC you have seen? So here is a minus 3. This is what the ROC you have seen. Next, another signal x of t, that is e power 3t u of minus t. Then we got ROC which is in this form. This is 3 sigma. This is what the ROC is. This is what the ROC is. Next, suppose if x of t looks like this, then ROC is entire S plane. Entire S plane. So these are the 3 things what we have seen till now. Here we can make some conclusions on ROC. What is that observations we can make? Let's see. First, if you observe the first signal what I have given here, it is a right-sided signal. U of t means it is a right-sided signal. For that, we got ROC which is a right-sided ROC. That means actually this minus 3 indicates pole. So here it is a right side to the pole. Next, x of t is nothing but e power 3t u of minus t, which is a left-sided signal. Here the pole is nothing but 3. We don't know what is the pole here, but still I am saying this is the pole. So just to make you understand what exactly ROC. So I am saying this is the pole 3. And here, because it is a left-sided signal, we are having ROC which is left side to the pole or less than the pole. Next, if I see the signal, the nature of the signal is like this. It is a finite duration signal and absolutely integrable signal. So if it is a finite duration and absolutely integrable signal, always ROC is nothing but entire S-plane. And one more thing. Will ever ROC have pole? No. Never. Never ever have pole in the ROC. Why? Suppose whenever I say ROC, what do you mean by ROC? It is a region of convergence. That means Laplace transform should never go to infinity. That's what the meaning of it. So if I substitute pole, suppose let's say 1 by s plus 3. So for this one, actually the Laplace transform is 1 by s plus 3. This is what x of s. If I take s is equal to 3, s is equal to minus 3, then what will happen? This value will become infinity. So can I simply say ROC should never contain any pole? That's what the meaning of it. ROC should never contain any pole in it. Why? If you take pole, at that pole Laplace transform will become infinity. So I hope you understood. So these are the points what we have to write. So first take them, then we will write one by one points. Properties of ROC. The first property, ROC should not contain any pole. ROC should not contain any pole. This is the thing one. Next, for right-sided signal, ROC is greater than the pole ROC is greater than the pole. That means here if it is a right-sided signal, so what is the ROC? Sigma greater than minus 3. Next, for a left-sided signal, ROC is sigma less than 3. Okay, so here third point. For left-sided signal, ROC is less than the pole. Less than the pole. Next, for finite duration, and absolutely integrable signal, ROC is entire S-plane. ROC is entire S-plane. Next, fifth point we haven't discussed yet, but still you can write it. For two-sided signal, ROC lies between the poles. So this is what the properties of ROC, 5 properties. You can remember them easily. Okay, take it.